Hello and welcome. My name is Eliezer de Souza da Silva. I'm a PhD candidate at the Department of Computer Science, Faculty of Information Technology and Electrical Engineering. I'm supervised by Helge Langset and Harry Ramapiaro. And in this trial lecture, I will talk about explainable AI for recommender systems. We'll discuss the state of the art and current trends. As an outline for this talk, we'll start with an introduction and motivation with general principles and taxonomy for explainable AI, challenges in explainable AI for recommender systems, approaches that we find in the literature, and with that in mind, we'll focus on a specific subset of methods in the literature. We call it contrastive explanations or counterfactual and causal explanations. And finally, we will conclude with some remarks and perspectives about the area. As an introduction, we can think about recommender systems as systems capable of adapting and adjusting automatically based on user behavior and based on the user information needs. So these are systems that can basically have as an input the different interactions between user and items, ratings, or number of times that a user clicked a given item or attend to a given item. And from that input, the system can try to predict what other set of items the user will in general be interested in. In that sense, the system is trying to predict an information need, but as a consequence of that, also many of those systems are black boxes with respect to how this prediction is done and why this prediction is done to a given user at a given time or in a given context. This reason for being a black box is mostly because it's focused on explanation in prediction, and prediction in a sense is the only metric being used so far in many of those systems. So in that sense, we would want to include other goals and tasks or metrics to evaluate the recommender systems. And in this case, this one important goal here is to obtain explanations for the user as well. So there's a set of many methods in the literature and graph-based recommender system, matrix factorization, neural recommendations. We're not going to discuss in details each of the techniques, but just to mention that they exist. As a motivation also, we'll enumerate the why or reasons that explanations are important for recommender systems. One reason is that to increase trust of the user in the recommendations. So this is a very important goal in a sense, because given that the user might not understand why a given item is being recommended to them, they would distrust that recommendation. So if there's ways to explain to the user why this item is being recommended, we would expect that the trust would increase in that case. Together with that aspect of trust, there's the aspect of transparency. So not only trying to increase trust on a given recommendation, but also trying to explain in details how the system is doing that. So there's details that how the system might be doing that are possible to disclose to the user. And of course, also there might be details that are not possible to disclose to the user, but in general, it's an interesting goal and good goal to have. Also, another goal here is control or controllability. In that sense, the idea here is that if the user understands how their action, so a choice of interacting with a subset of items, leads to certain types of recommendation, they might be able to control the interaction or better control the interaction between the user and the recommender. And this is an interesting also ability to give the user, and also it's a interesting feature for the system to have, because it will become more interactive with the user in that sense. Scrutability, this is about the by giving explanations, we allow the user also to isolate incorrect, possibly misguided assumptions that the system might have. So this is the case that in some situations, a recommendation together with an explanation would be enough for the user to examine the assumptions and be able to tell, well, this assumption is not correct, for example. Persuasiveness, here it's about increasing the acceptance of the recommendation, so the system being persuasive to the user. This goal alone shouldn't be, say, a goal on itself alone, but together with other goals such as trust, transparency, it's an important goal as well, because we want the user to believe in the system, or in a way believe in the recommendations that are being given, because they trust the reasons that those recommendations are being given to them. Effectiveness here is about being able to assist the user in making better decisions. So again, if the user understands why the system is given certain recommendations, this will inform also the user in how they make their own decisions as well. And as a general goal here, satisfaction, which is also an assumption that by being more clear about how the system is generating recommendation, the user might have a better experience with using the system. So in general, the assumption is that when we don't understand something and we interact with something we don't understand, this might be a bit not a very enjoyable experience. So those goals have been collected and discussed in more details in this work by Tintareff and Mastov. So we recommend you to read more on that. General principles here. So we discussed a little bit some possible goals that would be interesting to have on our explainable recommender systems. Here we want to rely in intuitions that are coming from the social sciences to try to think from a broad perspective, what could be good principles to have in a explainable recommender systems. So we rely here on the work of Miller in the Artificial Intelligence Journal. This is a very interesting work where there's a broad discussion about explanation from the point of view of social science, behavioral science, and psychology, and how those, or in a sense, trying to understand how humans, or how we consume explanation or generate explanation, and what properties of those explanations are interesting for us as users or as humans. And as an overall conclusion, we underline 4 properties here that we think we can consider general principles for explainable AI when take into account this input or these insights from social sciences. First is explanations are constructive, contrastive. Here, the idea is that a typical explanation that we enjoy or we engage with are explanations that make contrast between 2 scenarios. So the reason that I'm doing this is because of that, but also if I did something different, I would get a different result. So having this sort of contrast between scenarios and how they generate different outcomes. This also informs a bit these goals of being scrutable and actionable in the sense that how changing a certain scenario leads to a different result. Also, in this work, they underline the idea that explanations are selected in a biased manner. This means that we tend to enjoy or like explanations that are concise and short. And even if we are given a long list of possible explanations, we would tend to attend to a small subset of those explanations. So this also informs how explainable AI could generate explanations in a sense that it would should consider always small sets of explanations. There's a comment that probabilities probably don't matter, and the way I understand this is that the exact numerical relations here might not be super important for a human reader or someone trying to understand an explanation. And probably more important is the linguistic and logical connection between the elements of the explanation. And explanations are social, so we engage with explaining things to other humans, and we understand explanations often from this point of view of being explained by other people. So we should expect that human agents, when interacting with explainable AI, they will assume or they will anthropomorphize certain aspects of those explanations. So these are general principles, and they should inform us in a way and be sort of important guidelines to keep in mind. As a general taxonomy here for explainable AI, we also rely here on literature and Sogeti Labs diagram of a way to think about this. We can think about post-hoc and anti-hoc types of explainable AI. The basically difference here is that in one case, we have explanations that are generated after the model or a black box model or an opaque model has been fitted on the data. So this line here, we have a data model fitting, opaque model is generated. Then we create, for example, a surrogate model or some other methods of explanation, and we generate explanation. And Antioch are models that by design, in a way, are already interpretable and generate explanations together with the predictions and together with the training data. So these are basically two different ways to look at it, and we'll also use this terminology in different points of this lecture. In our view also, we can think of explanations in two different ways here, in particular also for recommended systems. We can think of explanations in terms of how the internal working of the system is reaching a certain ranking. So these are explanations that would focus on interaction between items and how one item leads to another, or for example, or graphical relations between the items, or this sort of techniques, but fundamentally trying to explain how the system is navigating from different choices to the final result. Another set of explanations, we think in terms of how the user actions will impact the recommendation. So this is related to this idea that the user, we can inform the user that a given recommendation was given because the user liked a given thing or purchased a given item. So this is about which actions the user took that led to the recommendation, and not much about the details, internal details of the system in reaching that conclusion. Also, we highlight here a long list of modes of explaining that we find in the literature. We'll briefly mention some of them. For example, there's textual explanations, both based on natural language and also based on topics or word cloud or tags. So there's multiple lines of research and multiple papers. We just cite some here just to reference that are based on those techniques. So this in general means that the explanations are used together with, say, a language model or a topic model, and they try to basically generate the explanations that fit those models as well. There's also multiple methods that are based on finding examples on the training set. There's both in the sense of finding certain attributes or features that are important for the explanation, or specific data points that are important for the explanation. We highlight also that there are some model-specific or we call it logical-based explanations. So, for example, in Bayesian networks, in this sense, there is by design, the model allow for inspection, and for in that sense, there are algorithms that we can apply in the model and be able to come up with explanations based on the model properties and exploring basically how the model reached a certain conclusion. So there's a rich literature on that, which is also again mentioned some just to have a reference for you. And more, there's multimodal and heterogeneous type of explanation, visual-based explanation, graph-based explanation, context-aware explanation, explanation combining different modes. And we refer here for the great survey of Zhang and Chen that covers all of those and multiple other ones. So as overall challenges here that we can identify the following. Opacity of the system. In this sense, we are in this initial setup that we discussed. Systems are black boxes, but also there's different levels here of opacity. So taking that into account, so different models with different levels of opacity, they will generate different sort of solutions. So this is a challenge to take that into account, either a full black box model agnostic or some system that can inspect some certain aspects of the model, for example, the weights that were trained or such. So there's different levels of opacity here, and they, at each of those levels, they will generate different challenges in terms of the methods. Fundamentally, this is a problem with human in the loop. So the explanations, they cannot be fully evaluated on their own. We need to be able to have the feedback from the user in some way. So there's the need of this feedback loop here. So there's no way to avoid that when we are talking about explanations. So this should be a fundamental part also of the thinking around this topic. There is also potential trade-offs between explainability and predictive performance. So this is relevant particularly for systems that are designed to be explainable from the ground out, so the Antioch systems basically, and in that sense there might be those trade-offs, and there's a issue of trying to identify them or finding the optimal trade-off between explainability and predictive performance. And overall, we have here a large space of possible solutions and large space of possible more complex and less complex solutions. So being able to identify and categorize the complexity of all the solutions and what is the requirements and what requirements leads to less or more complexity is also a challenge in this field. We list also some overall computational challenges. So here, one way that we can think about this is that there is a search problem of going over a space of possible explanations. So as we discussed and mentioned before, there might be multiple possible acceptable explanations. So the system needs to explore that space and find those multiple acceptable explanations for a given outcome or a given recommendation. In that sense also, there might be potential time-space trade-offs. So for example, a system might keep traces of how it was trained or how the interaction between the items happened during training or even during inference time. And by keeping traces and saving this information, being able to reduce the complexity of this search problem over the space of possible explanations. Also, it might be a problem where we have constraints as well. So it's not just search of a possible explanation, but also identifying these constraints and respecting those constraints. One very important here is privacy and protected attributes, because recommender systems are typically trained on collective data. So not only a single user data, but typically many users and many items and interaction between many of those. This basically exposing all the inner working of the system is a risk to expose also private data about from different users to other users. So there's constraints here on this solution space on what can be disclosed or what can be included in the explanation of our system reached a certain conclusion. So in that sense, there's constraint satisfaction as well. In another sense, so we might have a subset of acceptable explanations according to certain criteria. It can be aesthetic criteria, it can be, for example, linguistic criteria, and it can be also logical criteria that we impose on top of a set of the possible explanations. So this also inform the computational problem here. This is very important in the case of recommender systems, is that we are treating with subsets or set of items. So the problem is necessarily combinatorial. So a lot of the solutions that we'll see, we can think of them are, they will be approximate solutions, because exact solutions that explore the possible space and satisfies the constraint is going to be very big, will be exponential potentially. And another related, but maybe more specific problem here is the problem of relevance propagation in neural networks. So in predict assignment or attribution, this is a problem when we are using neural networks for recommendation, and in that sense is the issue of how to find which features in the layers of the network are responsible for a given ranking. So we'll discuss now some approaches in the literature. We'll start with what we call the Antioch explanations, or explanations by design. So in this case, as we explained before, the main assumption here is that we create models that are able to, while given recommendations, also be able to create explanation about those recommendations. And we highlight here a work that is based on neural networks and basically VAE architecture, where the system is developed such that there is both this propagation of attributes or propagation of weights and how the weights influence each other, but also there's a model of this influence model on top of basically the calculation of the final ranking. So the model has both a propagation of influence and an influence model where they can attribute why a given ranking was outputted by the system based on different attributes, both from the input, but also potentially from internal nodes of the system. So this is this idea of attribution and disentanglement of latent representation in the work of Liu et al., recent work also in 2020. Another set of approaches that we find in the literature is model agnostic. In that sense, we can think of basically two strategies here. One is the strategy where we create surrogate models. So the system will take a trained model, so as an input as well, and together with this trained model, it will try to create explanations, and usually by creating a surrogate model on top of the trained model together with, for example, extended data set that includes also explainable information. So this is a technique that was developed by Ribeiro et al. Called LIME. It was published in 2016 for, in this case, for a classification problem, but it has been extended also for recommender systems. So LIME, a recommender system by Nóbrega and Marinho, and LAIR by Chansot et al. Those are extensions of this idea of surrogate models for the context of recommender system. Here we reproduce a figure from Nóbrega and Marinho, where they explain how they apply the LIME workflow in recommender systems. So here we can see that there's a trained model with user embedding and item embedding, one-hot embedding, genre embedding in the rating. The model basically predicts the rating based on those embeddings. And then we have a surrogate model here, which is this LIME. This model will have this idea of permutations and basically small local variations on the training data, and generate also now explanations in terms of, for example, generally why a given explanation it was given is because it has this, why a given recommendation was given is because it has this genre. So this is the idea of surrogate models. There are also some other strategies that can be used. So for example, there's strategies based on search. So in this case, there's not a creation of a surrogate model, but basically an algorithm or a methodology for searching on top of the training set or a subset of the training set or the item set, basically, to try to explain how this subset is related to a given recommendation. In this case, the work of Cafes et al., they use a counterfactual criteria, which basically says the model is trying to find, so it's a search procedure trying to find a subset of items that can explain counterfactually a given recommendation. So finding a subset that if we change that subset, we would obtain a set of items that from compared to the training set, if it was different in a certain amount of items, we'd obtain a different recommendation. This is a search based, so they deploy different strategies here. So they random search, breadth first search, and different search methodologies. Yeah. And finally, we want to discuss a little bit the contrastive explanations. So this also is highlighted by Miller, and as we discussed in the beginning. So the idea here is that the general question is why outcome A instead of B, and here we can talk about also counterfactual explanations based on a set of actions of a user that if we change or remove certain actions or change certain actions would generate a different recommendation. So we can think here that there's a actual history of user interactions with items that generated a given recommendation, and then there's counterfactual world, so different possible histories of interactions that would have generated different sort of recommendations, and those different set of actions would serve as a counterfactual explanation. So here we'll highlight some works that use counterfactual and causal analysis in this contrastive way. There's the work of Tria and al. 2021. So here, as we talked about, there is a real story of a user interaction with a certain amount of items. Recommend the system recommend a given item, and then the idea here is that the model will explore a counterfactual history. So it will generate variations on the actual history, so perturbations on the actual history of the user and try to see which perturbation leads to different recommendations. So for example, here by perturbing the item I3 by I8, there's a different recommendation given. So we might then conclude that item I3 is in a way explaining the recommendation that was given. So this is the idea here. Other works explored similar ideas, but extending them in different ways. So here we have the work of Gazimatin et al. In 2020. So it's called Prince. This work explore this idea of counterfactual explanations as well, but also includes this idea of heterogeneous item network, so different interaction between the network, but that they cannot be disclosed to the user. So again, this talks about protected subsets of items or the subset of how the system see the relationship within the items. And because of, say, privacy issues or different issues, they cannot be disclosed to the user. So this approach tries to take that into account and also generate counterfactual explanations. So for example, here, the example is given is that would be like, if given a set of actions that a user took, if each of or any of those actions was changed, the recommendation that was given would change. So it's trying to find a minimal set of user-specific actions to change the explanations, the recommendations. And finally, also, we highlight here the work of Tria et al. 2021 called Accent. In this case, it's a counterfactual also explanation, but it takes into as an input as well the parameters of a neural network. So those previous work here, this we don't take the parameters of a neural network. This is this heterogeneous interaction network. And in this work here, there is this idea of taking the parameters of a neural recommender system, but also with the same goal of generating explanations that are based on these counterfactual scenarios. So to conclude, we have seen a different set of techniques. We have looked on important features that we could or are necessary to include in explanations for recommender systems. And what we think also as a future direction and different threads to explore, I think it's very important to look into cognitive and social science, such as the work of Miller, but potentially new exploration, new works on that line, mostly because fundamentally we want to generate explanations that have a value to the end user. So I think this is really important and interesting goal to pursue. The generation of explanation using natural language, there's also a lot of growth or possible growth there. And here we highlight some work that are being generated in the NLP community. So these works are mostly focused on NLP. For example, the idea of explanation games. So this work here by Treviso and Martins, the idea here is that you generate an explanation. So there's a classifier, there's an explanation for a given classification, and then a second player on this game will receive the explanation and generate a classification as well. And if those tags of the classifications, they match, it means we can use that as a good signal for the quality of the explanation. So this is thinking about explanation as a game and also as a communication game between two actors. And this is interesting also because it can be used even from machine to machine. So it's a conversational explanation, both between different machines, but also mostly between machine and humans. So this is also a highlight here, work of Ribera and La Pedriza in terms of conversational explanations. Also, we highlight the direction of causal and neurological reasoning. So the reason that this is very important is because explanation are rooted in being able to think logically and have structure on terms of how a given decision is taken. And traditionally, how a lot of the machine learning methods have been working is by relying a lot on prediction. So we do need to go deeper into explaining those predictions in terms of logical structures and causal structures. And here we highlight also work of Karimi in 2021, where it's developed counterfactual explanations that leads to intervention. So as we discussed before, a lot of those counterfactual explanations are interesting, but they don't have a strong emphasis on intervention. And in this work here, they develop this further in the direction of intervention. So really trying to think what interventions the user can make in order to change the results. And the explanation is going to give this type of interventions to the user. So in general, this is some of the possible directions and perspectives that we see. And we thank you for your time, and I hope you have some questions for us. Thank you.